So everyone, a real treat for this week. Someone I'm afraid to say I'm a bit of a fanboy of myself. So I'd like to introduce Professor Ronald, who is here from ASML. I hope you guys, when you had the chance to see some of the pre-reading, to see quite how, in some ways, magical the technology is, and the fact that it is the piece of equipment you need to design all the modern high-performance semiconductors, like in my cell phone and laptop, and in all your cell phones and laptops. So without further ado, I'd like to invite Ronald to come on over and take away a lecture.
Thank you. And you can all hear me? Well, excellent. Well, it's a pleasure being here, and I look forward to spending about 45 minutes with you, and then hopefully some time left for questions and answers. I know you guys have ladies already heard quite a bit about changing the world with chips. I'm going to take the perspective today about what is actually going on in the equipment industry that supports the semiconductor manufacturing. And given the fact that I am with ASML, I'm going to spend a disproportionate amount of time on lithography, because after all, lithography is really a cornerstone technology for manufacturing. Let's see. Is this? Yeah, now it's working. So first, a few things about myself. I am originally Dutch. I got my degree in physics and astronomy in Europe, in the Netherlands. Worked for Philips Research, and then had an opportunity to come and work for a year and a half at Stanford University. Well, I promised my wife it's really, really only for a year and a half, and that is now 36 years ago, so I guess I liked it here. Since then, I've worked for National Semiconductor, for Semiconductor Research Corporation in the 1990s. That's where I first met Professor Lundström, so we go back a long time. I've worked for Philips Semiconductors, and now the last 20 years for ASML. The constant theme in my own professional focus has always been on modeling and simulation. And that started already with in my physics time. Then on transistor modeling, I did circuit modeling, I did whole system level modeling, and the last 20 years really looking in more detail at lithography. I have a whole bunch of hobbies. That was one of the reasons why I had to retire from full-time work. I needed more time to pursue those, and just came back a few weeks ago from a week of motorcycling in northern Italy, so if you like stuff like that, come and talk to me afterwards. I've really been privileged that when I started my career, I was working on 3-micron technology. And can you imagine that here, nearly 40 years later, I finished my professional career working on 2-nanometer technology. And it's really a privilege that I happen to have been born at the right time to be able to be on this incredible ride called Moore's Law, but it hasn't finished yet. There's still a lot to go. Let's see. Yeah. So let's start quickly with a video on how do you make a semiconductor chip. Let's do it that way then. There we go. So here you see the dies being in the package, and of course the die is just one of the many fields on this wafer. Now we start to zoom in, and we keep zooming in, and we keep zooming in, and ultimately we then can start to see the patterns that are built there. And when we zoom in even more and we get kind of a sideways view, we actually realize that just the interconnect can already be tens of layers of metal interconnect, and below that, of course, is the transistor structure. So it's quite a complex thing, those semiconductor chips. This somehow is not really working very well, but we'll get there. Now these semiconductor chips, they come in many, many versions, and right now I think that there are 3 very important forces in society. First of all, more and more we live in a connected world. We all have our phones, and they are now 5G connected. That means that there is a lot of computing going on in the cloud, so cloud infrastructure, we hear about that. But also now edge computing, much more of the data, in particular sensor data and so on, that gets processed. So there is really a plethora of new devices being conceived simply to support that connected world. The second big movement is, of course, climate change and resource scarcity, which means we see a lot of electrification going on. We see energy transition going on. We need to make sure that our agriculture is productive, and we see usage of sensors and GPS and automated irrigation systems. And there are large social and economic shifts where, with COVID, we all learned to work remotely. That was a big shift with a lot of new demand for chips. Healthcare. Healthcare is becoming so much more potent thanks to technology, and a lot of that technology involves sensors and chips. And I was earlier today in Berg, saw some fantastic work that is being done there on micro robots for precision delivery of medication and so on. And of course, there is also the whole discussion about technological sovereignty. We know about the CHIPS Act in the US, and that we want to make sure that we bring more of the manufacturing back to the US, that we're not completely dependent on foreign countries in Asia for our semiconductor production. Now, all of that leads to a market where we think that by 2030, we will probably have a market that just the semiconductor sales is already $1 trillion per year. And if we then look at where is all of that money being made, here you see a graph of all kind of companies, and many of these companies you will recognize. The area of each of these blocks is proportional to their EBIT, the earnings before interest and taxes. It's a well-known economic measure for how much money does a company make. And the ones in gray are actually the ones that didn't have earnings in 2023 but actually had losses. So 2023 was a tough year for semiconductors. 2024 is still a little tough. Probably 2025 we will start to really see an upturn. Certainly AI is helping, but it's only helping for certain parts of the market. Now all of that demand is of course supported by Moore's law, and we create more and more transistors. Here you can see that we're on track, that probably by 2030 we will be able to have a staggering amount of 1 trillion transistors on a single chip. That's staggering. What's even more staggering is that the demand for compute is outpacing that progress of the number of transistors. We need to do much more to feed all this hungry beast called AI with compute power than just following Moore's law. And to give you a sense here for how bad that is, one of the supercomputers that is being used to train some of the largest language models is called Aurora. It has the staggering capability of 2 exaflops. Now, when I started, I told you that my whole life I've been into computer modeling and simulation. So I grew up when megaflops was what we counted. And then a little while later, we started to count gigaflops. And then it became teraflops. And then it became petaflops. And now we're actually talking about exaflops, 10 to the 18th floating point operations per second. That's a staggering amount. But it doesn't come without cost. There's big cost involved. Look at it. 58,000 CPUs needed for this one supercomputer. Total cost $500 million just for this one supercomputer. And in terms of energy consumption, because we also live in a world and you are all a generation that is worried about climate change and you want to be responsible also ecologically, this thing is going to use 60 megawatts and consume 34,000 gallons of water per minute just for cooling. So we obviously need to create more compute power, but also in a sustainable fashion. What does that mean from a device logic perspective? Here you can see what we've been doing with transistors, and I hope that all of you have by now heard about the MOSFET, the planar MOSFET. So you have a source here and you have a drain here, and there is a channel region in between with a gate on top, and that gate controls whether the channel region will conduct the electricity from drain to source. That was, off the chart on the left-hand side, the planar MOSFET. Then somebody had the smart idea that they said, in this width direction, that determines how much current capacity that transistors have. If I pick up that transistor and I fold it up like this, and turn it into a fin that stands up, it takes far less space. That became the FinFET. We've been making those since 2018. The problem with the FinFET is you get one height. So you get the equivalent of what used to be one width. In your design, you can no longer choose the width based on what you need electrically, other than simply putting two of them in parallel, or three, or four. But now your space advantage is gone again. So then they came up with the idea we can change the transistor architecture into nanosheets. Let's take this fin, flip it upside down, and now in addition you can also see there, let's see whether I can point that carefully for you guys. Yeah, you see that here every gate is only surrounded on three sides by gate material. So there is a limited amount of electrostatic control that the gate has over the conductivity of the channel. Because from the bottom, there is no gate there. So it's very hard to stop the electrons from going from source to drain at the bottom of that channel in a FinFET. Having flipped it, you now see that here, you can have a gate all around. These nanosheets are also often called gate all around transistors. So now I have better off current. That means that I can operate at lower voltage. That helps with less power consumption per transistor. It also can make them faster. And I can build a good current capability simply by stacking a number of these sheets on top of each other. And once I know that I can do that, I can go even further. And this is in the future, around 2030, we think that the so-called CFETs will come. What if I start with a number of layers that I call an N channel, and on top of that I build a number of layers that I call a P channel, and you can see that all of the gates are connected. Wait a minute, an N channel and a P channel with the gates that are connected? Oh, I've made a flip-flop. So now I get the flip-flop, a complete logic element in the space of just one transistor. So you see that circuit architecture and transistor architecture really helps with scaling in addition to making simply things smaller. And there is a lot of work being done by Zhihong Chen in the Burke Center, and now that Purdue also has a collaboration with IMEC on 2D materials, that when these sheets get even smaller and thinner, 3D materials, if you make them very thin, they stop conducting electricity, but there are different types of materials that are extremely good at conducting electricity at the moment that you make them basically atomically thin. So that's something that we think by the end of the 2030s, early 2040s, there is plenty of runway for further innovation in this field. From our perspective, we know that we need to make these chips, and that's a big process, right? You start with depositing a layer, you put the photoresist on it, you put it in one of our machines to pattern, then you can develop the resist, you etch it, perhaps you have to do some ion implantation, you remove it, you do inspection, you apply the next layer, and you do that up to 80, 100 times. The more we can simplify that, the better off it is. It makes it cheaper, it makes that you can make things denser, and that means that you get more compute power for less electrical power and also less money. I have a lot of material, so some of the things I skip over. All of the slides will be made available as a PDF. So if I go a little bit fast, don't worry about it. Just try to pick up on the key ideas. So what I'm showing here is out of that whole process flow that I showed here, out of all of that equipment, where is the money being spent? Well, you can see that a very large part of the money is being spent in lithography. A big part also in etch and in clean and in deposition tools. A little bit also in CMP, that's the chemical mechanical polish, to planarize surfaces after you've done some patterning. And you have the ion implantation, and you need to continue to test them. If we look where our customers really spend their money, if you build a new fab, and you know that we're now sponsoring in the US new fabs being built by TSMC, by Samsung, by Intel, hopefully by Global Foundries. But an advanced fab nowadays, by the time that you're done building the building and filling the building with all of that equipment, you've probably spent $25 to $30 billion. And the brick and mortar is a very, very small fraction. The overwhelming part of that is simply semiconductor equipment. You see that here. And with that, we can then, in the end, build a structure like what you see here. Looks a little bit like an apartment building. All the way at the bottom, you see those transistors. They are very, very tiny. At the lowest level, they all get connected with very fine... volume up a little. Okay. So at the lowest level, the transistors. Above those, you see the local interconnect to connect all of the cells. And all the way at the top, you see power distribution and long-range connectivity. One of the things that I've not talked about, but that is interesting research that is going on, what if I could forget about that power all the way at the top? Because every time that I have power at the top, and I have a transistor here, I need to bring that power all the way down through this deep stack. Every time that I use up area in this layer to bring the power down, that's area that I cannot use to connect the transistors with each other. That's called a routing conflict in EDA terms. What if I could use the front side only for connectivity, and when I'm done, I flip the whole wafer over, I make it really thin, I drill holes to the transistors, and I build the whole power distribution from the backside. And what if I could then flip it back up and drill more holes on the front side, and now put complete memory packages and other things on top of the logic chips. So that's some of the advances that also here in Purdue, there will be a lot of research happening in advanced packaging. Purdue is very aggressive in that, and that's one of the reasons why Hynix was interested in making their big investment in this region. So I'm just trying to connect those things for you all together. But let's look now a little bit more at a little bit of that same thing here. So we're zooming in. We're zooming in a little bit more. And now we're going to look at what are we actually trying to build. Here are some SEM pictures of an actual structure that you can build. This is really at that lower level, the lowest level of interconnect, right where you see the transistors. And what you can, let's see, yeah. What you can see here, for example, is a good part of you need to have good overlay. Because this metal line needs to somehow connect to this metal line here. And we do that with this via this little contact hole that makes the vertical connection. You can imagine that if I put the metal line here in one layer, but the previous layer was mismatched, and that via sits here, hey, I have very poor connectivity, right? But look at the small contact area. That's never going to work. What happens when I have a small contact area? I have more contact resistance. The chip is slow, but I also get more heat dissipation. That means that it ages over time. I get lifetime issues with electromigration and things like that. So overlay, making sure that every layer fits perfectly on top of the previous layer is absolutely crucial. On our machines, we typically try to achieve an overlay, a total overlay from all contributions of about 3-4 nanometers. Our own machines should contribute to a total budget on overlay because there are stress effects, there are all kind of other things happening. mask may not have been made perfectly, our machine should contribute less than half a nanometer of overlay. Let's look at that in a little bit of detail. One of these server chips used for AI nowadays can be 800 square millimeters in size. In 1 square millimeter, because we can make things so small, we can have 100 million contact holes. Those little connections that I just showed you, those vertical connections. That means that just on one chip, I can have 80 billion transistors. 80 billion contact holes. And here you see that for some silly reason, whether it was an imperfection in the resist, or just some statistical fluctuation in the number of photons, this one here did not open up very well. And we're really looking at, we need to control 80 billion of these things. So in this whole lithography, or in this whole chip manufacturing loop, lithography is incredibly important, because first we need to get 80 billion of those contact holes right in one die. Then we need to make sure that we do that for all 200 die on the wafer. Then we need to make sure that it works for all 200 wafers that we produce this hour. And we do that 24 hours a day, 7 days a week, non-stop. 95% of the time the machines are running. So the level of process control is really outrageous, and I don't have time to go into the statistics of very extreme events that happen at 10 to the minus 8 and how you calculate and then control that. But there's a whole bunch of interesting industry. Our value from our side, we try to keep that really very simple for students. And can I have a quick check on time?
16 more minutes.
16 more minutes? Okay, good. So we try from our side to be very simple in our proposition on our value as a company. We provide value by making sure that there is very good patterning yield, by improving the resolution, by making sure that the CD of the patterns and the overlay is very good, and doing that hundreds of times per hour. That's our value. Our value gets less the more expensive we make it, unless as it gets very expensive, the lifetime is also really good, because it's really the cost of the equipment per year, that is your depreciation, and operational cost and environmental cost. I can go into each of these and tell you for hours about stunning innovation that is really world-class in each of those domains, but I'm just going to pick a few examples. Let's first start with the resolution. So the half-pitch, very famous formula, K1 lambda over NA. The lambda is the wavelengths of the light. K1 is the factor that describes how good we are at doing complicated stuff. And the numerical aperture is basically how big is the lens that you use to project the image. The bigger the lens, the more of the diffraction orders gets captured. In my class, I will teach that has something to do with Fourier optics and how many Fourier components you capture of the original mask pattern. And so the more components you capture, the more accurate is the recreation on the wafer. We used to use argon fluoride immersion lithography with 193 nanometers. Now we use EUV lithography with 13.5 nanometer. By the way, everybody aware, right? 400 to 700 nanometers is visible light. This is ridiculously shorter. We call it EUV. You actually could call it soft X-ray, but we don't. That sounds so scary. So the NA is that opening angle, and the bigger I make that, now there lenses have the advantage because we've been doing that for a long time. So lenses have a higher NA, but also a much longer lambda. On the EUV side, the current generation of tools uses a numerical aperture of 0.33, and the next generation of tools, where I will show you some examples, is going to 0.55. We have a lot of experience with deep UV lithography, and we're very good at doing complex things there. It's a little tougher with the UV, but when you add it all up, here you can see that we've moved from 76 nanometers pitch. I have a pattern here. How far away is the same pattern? The half pitch is how big can I make this pattern, how big can I make the gap in between. So those numbers you see there, and you see that it's really quite stunning that we were actually able to make 8 nanometer features every 16 nanometers. So how do we do that? Here you see on the right-hand side a quick sketch of a very schematic sketch of a scanner. You have a light source. You have an illumination system that makes sure that the light hits the reticle, the mask, nice and uniformly. The light diffracts off all of those patterns, goes into the projection lens, and the projection lens gathers the light and focuses it on the wafer. We optimize the shape of the illumination. We optimize the polarization of the light. We look at what is exactly the dose that I need to get the right CD. We look at mask optimization. The mask gets treated in OPC. That's also one of the classes that I will be teaching. The projection lens we try to make better and better, and of course focus control is really critical. Again, harking back, I started in the early 1980s, 3-micron technology. Here you see a resolution of about 1 micron in 1985. By now we're looking at half pitch or at a resolution of, as I said, 16 nanometer is pretty much now with the high-NA tool doable. That high-NA tool really gives a pretty big step in the numerical aperture. You can see that by going from the 0.33 NA to the 0.55 NA, we actually get an improvement from 67% in the NA, 67% in the resolution. That's a very big step in one go. Here I'm showing that I don't want to leave you with the idea that all these 80 layers are all made only with the most advanced tools, because you already saw that the bottom layers are the ones that are the finest resolution, and the top layers are much rougher, are much larger dimensions. So for every layer, the manufacturers will use the tools that are appropriate for that layer, and here you see, depending on the market segment, what are the typical tools that they use. I already talked a little bit about where the visible light is and where we are now. So let's look for a moment at the system. This is a schematic of one of our EUV systems. Here you see the light source, and I'll in just a second show a little bit more about that. The light enters into the scanner. By the way, the 13.5 nanometer light, it would get absorbed by only 1 or 2 millimeters of air. So the whole internal of the scanner has to be in vacuum. Otherwise, the photons would immediately get absorbed by the light, by the air itself. So in this vacuum environment, the light reflects off a number of mirrors. You can no longer use glass. Everything has to be with mirrors. Here you see the mask, the reticle, quickly going back and forth. It then is projected with the projecting optics here on the wafer stage that is also quickly scanning back and forth. So as the reticle scans, the wafer scans, and when we're done, we've exposed one field. We move over to the next field on the wafer. We scan again. We move over to the next field on the wafer, etc. And we can do that for 200 fields in 20 seconds. That means that, for example, that reticle here in our latest machine has accelerations of 40 G. Quite remarkable. And at the same time, while we're accelerating it so fast, we keep it in the right position to about 1/10 of a nanometer. So the large changes compared to the deep UV systems that we had were we needed a new light source for that new light. We needed a large vacuum system, and instead of refractive optics, we had to have reflective optics with mirrors. Let me show you this about the actual light source. You can't buy a light bulb with 13.5 nanometer light. The only way that you can get 13.5 nanometer light is if you create a plasma. that is so dense and hot that from the collision some of the inner orbit electrons get knocked out, and when an outer orbit electron falls to the inner orbit, it emits light of that short of a wavelength. How do I create a very, very hot plasma? Well, we take tin droplets that we fire with a few hundred bar. Then we hit them with an infrared laser a first time. They start to evaporate a little bit and oscillate. And when they're a flat platelet, they make a great target, and we hit them with a really, really strong second pulse of infrared light. These infrared lasers are basically of the same power levels that the military uses to shoot satellites out of space. That creates that plasma. You then have to capture all that in this mirror that you see and shine the light into the scanner. The mirror itself is a multi-layer, otherwise it doesn't reflect the light, and there is all kind of technology about plasma physics and surface chemistry. How do you keep this clean? Because every time that you hit that tin droplet and it evaporates, you can imagine tin splashes in all directions, and in no time all of your mirrors would be covered with tin if you didn't take care of that. By now, chips made with EUV, here you see a sample, are all over the place. I'm going to go quick because I want to show you the latest, some of the details here. So we have more than 100,000 individual parts. The thing weighs about 180,000 kilograms. 20 years we've worked on it before the product was ready, which, you know, for a company to continue to spend R&D money on a product for 20 years before it starts making money, that's in a capitalist world, that's not easy to do. You really need to be very visionary to do that. And just transporting them takes about 3 fully loaded 747s for one scanner. And that was the small version. Now we have the large version, the High-NA tool that you see here. We've continued to scale the source power. We can now hit 700 watts EUV light out of that source. The optics keep getting bigger and bigger, and you can imagine, you can see that here, that's an interesting detail. If I want to make that opening angle with which light comes in bigger, I need to make the mirror bigger. But then you have a problem, how do I get the light into that mirror in the first place? So we had to decide, we'll make a hole in the middle of the mirror, we'll shine it through the middle of the hole, we'll have a secondary mirror here that reflects the light and fills up this mirror that then finally focuses the light on the wafer. Here you see in Oberkochen in Germany, the large vacuum interferometers that Zeiss uses just to measure the accuracy of these mirrors. They have picometer surface accuracy. And then when you make mirrors that are that accurate, you also need to make sure that mechanically you control where they are sitting in your scanner and how you angle these mirrors. The angular control is large enough that if we'd had one of these systems and Neil Armstrong would still be up there and he accidentally dropped a penny, we could ask him, hey, do you want us with our laser to hit the left side of that penny or the right side of that penny? That's the angular control. Here's a video from Intel. So here you see the scanner arrive in all of these containers and being brought to Intel in Hillsborough. Here they are bringing it into their clean room. What you see here is just a base frame. All the other pieces still need to arrive and get assembled. Now you see the base frame being placed. We unwrap it. Next thing there is the source being put on top. Now the illuminator on top, and etc. You get a little bit of a sense of what incredible machines these are. What do we buy for that? Here you can see how much better the imaging is on that 0.55 NA system on the right versus the 0.33 NA system on the left. Better imaging, better accuracy, that directly speaks to the value. Those were the things that I talked about. Here you see the same thing now for a DRAM structure. So these are 15 nanometer contact holes, and you see how many and how close together, and how perfectly the imaging on each of those is. This is, by the way, not only imaging and not only machinery, just the resist was an incredible development. So we need chemists, we need mechanical engineers, we need many, many people. Yeah, we have a presence all over the world. Here are some of the sites. We are very broadly connected. We have a lot of partners. Some of those partners are universities. We now also do a lot of work with Purdue. We're about to sign on our 6th joint research project with Purdue, so we're very excited about that. And finally, I want to leave you with just an example of some of the skills that we need in our industry. So whether you're interested in chemistry and material science, or you're in computer science and software engineering, our scanners generate each about 4 terabytes of data per day that you need to analyze to be able to get to this level of process control that I talked about, so that's important. Electrical engineering, moving these reticle stages so fast, is power electronics with high voltage electronics, etc. I know that she cares about that. Logistics and supply management. When you move these reticle stages that quickly with 40G, how do you make sure that they don't vibrate and distort? There is a lot of mechanical engineering and again material science involved in that. I already talked about the optics and the physics. So I know that I had a great ride for 40 years in the industry, but if I look forward, there is so much innovation still to do and so much on this front. And it's fantastic that you're here at Purdue. Purdue has made a large institutional investment in saying, hey, we want to make sure that you can get the best education if you want to prepare yourself for a career in this field. So with that, we kind of come to the end of what I wanted to share, except for one thing. Since last year, I have an adjunct position here as a professor of nanolithography. So I'm teaching some 500 level classes. That's still a few years away for you. But in 2 or 3 years from now, I hope to see a lot of you in my class. It will be 3 modules, an introduction where I go into a lot of nanolithography. Then I spend a lot more time on the EUV lithography, and finally also on computational lithography. There will be 3 modules, each 1 credit, but by next fall, that will be all in 1 semester, so you can take them back to back as if it is a 3-credit course. If you say, hey, I only want to take 1 course to get a feel for it, you can just take the first course. So with that, I'm kind of done. Thank you for your attention, and happy to take questions.
Thank you very much, Professor Ronald. So I have some questions, but I'll look for taking questions from the floor. With the mic setup we have, I'll be walking over to you with the microphone. So does anyone want to kick us off? Anyone interested in asking the first question? Or I shall pick one from the list. Oh.
Why is 13.5 nanometer light, why is that the state of the art if X-ray machines have been able to make shorter wavelengths for a long time?
Yeah. Of course, shorter is better. The so-called L-band edge of silicon, which is where silicon starts to absorb the light very, very quickly, is at 11.1, 11.2 nanometers. So much shorter than 13.5 nanometer, and nothing would work anymore. The light would get absorbed instantly everywhere, in every material. And also really not go through any of the resist materials anymore. It would all be absorbed right at the top of the resist. So it had to be longer than that kind of minimum edge, and then you start looking for what has nature given us. We could have used xenon at 12 nanometers as an emission, but in the end that was very hard to deal with, and in combination with looking at What are the light source technologies? We came to the conclusion that this thin plasma was the best solution. And then the 13.5 nanometer is simply what is that particular transition of electrons from one orbit to the orbit in tin. That determines the 13.5 nanometer. Yes?
What has stopped ASML? I may have my answer just with the 20 years of R&D on EUV, but what has stopped ASML from really going into other market segments within the semiconductor industry?
Let me first talk about what has stopped us historically. There is a book that is now also available in English. So first of all, who has read this book, Chip Wars? Anybody? Yeah, quite a few of you? Okay. That describes what has been going on in terms of, the US starting, being leading, and now Taiwan being so strong, etc. There's a second book called Focus, and it describes the history of ASML. The leadership of ASML very early on decided, you know what, we are going to be successful by being focused. This already takes so much innovation that if we don't completely focus on this, it's never going to work. And that means that you bet the farm, because if it works, but there is no backup product that you're working on. But it also means that everybody knows exactly, hey, you better do your absolute very best, right? So historically, it's been absolutely focus. Looking forward, it's no surprise that while I have seen in my career things get 1,000 times smaller, you guys are not going to see that in your career, right? We're not that far away from an atomic level. There are a few hundred atoms involved in one transistor. Perhaps we can make them a factor of 10 smaller, but then we need to start stacking them. So stacking is becoming a big important thing. That's why there is now a lot of attention into advanced packaging. And if I package right now, the best packaging technology available is that I can take one die and every 10 micron, perhaps I can take another die and put it on top and get connectivity. What if I could make that smaller? What if I could do that on a nanometer scale? I could have thousands of times more connectivity between my logic chip and my memory chip, much more bandwidth, much faster computation, with much shorter connections, and therefore far less switching power. Wouldn't that be powerful? So we constantly look at opportunities, but we haven't put our dollars down yet on a particular bid. So basically, short version of the answer is focus.
Thank you.
I think we have time for a couple more questions. While you're thinking of those, I'll ask one that you submitted earlier. What are some of the technological advancements or research that you're looking at to improve the technology and cost effectiveness of your EUV systems?
Yeah. So some of the technological advances, the basic parameters are the same as they've always been. Make the wavelength shorter, make the NA larger, and make the K1 smaller, which is the same as saying get better at doing complex things. We need a lot of improvement, I think, still in resist technology. Resist typically tends to be organic long molecules. If you're trying to make things that are only a few nanometers long, these long organic molecules are really not that beneficial to you. The EUV light also is very hard to absorb sometimes. So nowadays we connect metal oxides to some of these organic chains. And these metal oxide groups capture the EUV light. They activate the ligands that are there, and that creates some of the cross-connectivity. There's a lot of improvement in the chemistry that I think we can still do. And I think that on the lithography side, as I said, another factor of 10 is doable, but then a lot of it will also come from packaging. And once I can think of, hey, inside one package, I don't just have a logic chip or one logic chip with one memory chip, but let's set our mind free. What if inside one package I could have 40 or 50 different die, all stacked together in some three-dimensional array? Then I can also get much more creative of what functionality do I put on what die. And then perhaps I can have one die with one process technology that is specific to communication, another one that is specific to memory, another one that is really good for very, very dense, regular computational that is highly parallelized, but another one is perhaps better for neural network type things. So you can start thinking of system level optimization in a very new fashion. So I think that we will see improvements in all of those.
Thank you. Anybody for the last question? So I have a question here on sustainability, which was how do the EUV lithography machines impact from production to end of life? And is ASML doing anything to try and reduce that?
Good question. It is a very serious concern for us. So first of all, about end of life of the machines. ASML as a company has now existed for about 40 years. And if I'm correct, more than 90% of all the scanners and steppers that we have ever made is still in production. So end of life is, customers say, hey, can't you keep maintaining this? We wanted to end of life some of the steppers. And the customer said, no, don't do that. Start a separate business just to maintain these machines because they really still work for us. So end of life is not a big issue, but sustainability and power consumption is. To give you a little bit of a sense, TSMC is this large company in Taiwan that does a lot of the production. A very good fraction of their power consumption is our machines. And that one company, what do you think the percentage of power is that they use in all of Taiwan? 0.5%? 5%? No, 20%. 20% of the power consumption of a whole country comes from one company, and I have to be ashamed that a very good part of that power is for our machines. So we have to do something about that. And how do you do that? Well, if you can make them more power efficient, then at least make them very, very productive. And make sure that they make more transistors, faster, more wafers. But there's also a lot of other things that we can do. There's a lot of cooling that needs to go on. When you make something this complicated, initially you don't worry about the cooling water. And by the way, that has to be ultra pure cooling water. So we have literally thousands of gallons of water per hour that is ultra pure water that just gets slushed away. That's crazy. You should retrieve the heat and use it for something useful. You should integrate into all of this a recycling mechanism so that that water can be reconditioned, so it's ready to be reused again for cooling. So on that front, I think that there is still a lot of work on sustainability engineering and industrial engineering that's simply driven by the fast pace of innovation we have ignored a little bit, and it has a lot of attention in the company now.
Thank you very much, Professor Ron.
All right. Anybody interested in, talking a little bit more afterwards? I'm happy to stay around. So, thanks everybody.
If I can stick in just one final word, imposter syndrome is a real thing. ASML, being the pinnacle of all these amazing technologies, may seem like a very frightening company to come and talk to. Please don't be afraid of them. In many cases, you're probably better than you know.